So last time I talked about lenses and a few concepts that I wanted to clarify this time around. The first thing I talked about was the fact that the lens was convex. And I said this was convex, and I just wanted to clarify what it means and what the opposite is. The opposite is concave, which looks like this. And I get this wrong all the time, so I figured I should make it very, very explicit what the difference between the two is. There is more to this, though, because in the last one, I only curved one of the surfaces. And you don't really have to do that. The important thing to take away from how lenses work, what it means to have focusing, is something else I sort of alluded to in the last lecture, which is that things that are curved have focal power. And what I mean by focal power is essentially the focal length. And I'll try to make this more clear for you. If I have some lens and it has a focal length out here, then all the light bends into that focus from light out here. Well, the amount of bending it has to make from an incoming ray is what we call the focal power. The more it can bend the light, the more focal power it has, and I'll try to show you what I mean. Let's make a lens that has far more curvature to it. So this one is far, far more curved, much steeper angles at the higher end of the lens. Now let's send in some of the same rays. And what happens is this ray at the top sees a much steeper angle than up here. So this light will get bent far, far more. And so will all the other rays, to the point where the light converges at a shorter distance. So the focal length is much shorter, f2, and this is f1. So f2 is less than f1. But in terms of the actual power of it, what we call focusing power, it's a greater amount. You can see that it's more powerful, it can bend more, and yet it has a lower focal length. Well, in terms of designing optical components over history, they didn't really like the fact that less is more, so they came up with a new metric instead of focal length for focusing power called diopters. And diopters is generally denoted this way, though most of the time you just see it written out as diopters. And diopters is just 1 over the focal length. So in this case, the diopters of the second lens would be greater than the diopters of the first lens. And since focal length is generally given in meters, this means diopters is actually just inverse meters. And this unit should have meaning to a lot of people because this is actually the unit they use in determining the power of the prescription for your glasses. They are literally calling out the focal power necessary in your glasses. The other thing that I want to emphasize is that it is in no means significant that I made one side flat in the previous lecture. Curvature of the same type adds together. In other words, if the ray comes through here and sees this first surface and starts to bend, and then it sees curvature of the same type on the other surface, it will bend even more. Meaning that this curved lens here would be, let me erase Let me erase this lens just to make it very clear. This lens, in terms of focusing power, let's say this is the diopters of lens 1, equals, if I just took, I really need to be able to draw this well to get the point across. If I just took the curvature of one side of the lens, that then flat, so we'll call this lens 2, plus a lens that has the curvature of the other side but is flat on the other. If we put these two together, it's the same focusing power as just the two curved lenses. So hopefully that makes sense. And the same is true for concavity. In other words, if I have something that is concavely curved on both sides, that is the equivalent of having flat on one side and concave, and flat and concave on another. Curvatures add in focal power. The other thing to take away from this is that curvatures of opposite type detract in power. So here we've got a concave and then a convex, or convex and then concave curvature lens. And this is the equivalent of having a convex with flat and a flat and concave. Now this lens here is the, we'll say this is the diopters of lens 6, and then we'll make a lens that is convex with the exact same curvature, and we'll call this diopters of lens 7. If these curvatures are the exact same, then they are the exact opposite of each other in focusing power. Let's actually put a minus sign in there. Yes. So this is the point I'm trying to get across. Opposite curvatures, opposite focal powers. So the last time I went into positive focusing power where light actually converges to a point. What does it mean to have negative focusing power? What does this mean? It means this. I'm going to make a concave lens, and normally you would say the focal length on this side of the lens would be here, like it was in these cases. But actually, because it's negative focusing power, the focal point on the right side of the lens will be on the left side of the lens. What does that mean? That's very strange, very, very strange. It means this. If we have an object over here, and we've got light coming to the lens, then I kind of lost my focal point. Let's draw that in red. Then the light coming out, perhaps this isn't the best example, would actually diverge as if it were coming from this focal point. Better example is, instead of saying this is an object, let's say this is just parallel light. That'll get the point across better than what I just gave. Give a better concrete example. Focusing a focal length on the opposite side of the mirror because it's negative power. When we have light coming in from infinity, light will then come as if it's coming from the opposite side of the lens and will diverge out. And so light that is diverging instead of focusing has negative focusing power or negative diopters. And that's it. That's what you need to know.